Saying, our AI must be fair, is like saying, our company must be successful. It sounds right, but it doesn't tell you what to do. We've already discussed ethical principles and how AI can harm entire groups of people. Today, we dive straight into the thick of it, bias and fairness. The goal of this lesson is to turn the abstract principle of fairness into a concrete, measurable, and manageable practice. We'll learn how to detect bias, measure it, and, most importantly, make deliberate choices about the inevitable trade-offs that appear along the way. Let's start with a story where more than a job is at stake: human freedom. In the U.S. justice system, the COMPAS program is used to help judges assess the risk that a defendant will reoffend. The intent seems noble: analyze someone's past and produce a risk score that influences bail decisions. But in 2016, an investigation exposed a disturbing fact: the system was wrong in different ways for different races. Among people who were released and did not reoffend, black defendants were almost twice as likely to be falsely labeled high risk. Conversely, among those who did reoffend, COMPAS more often mislabeled white defendants as low risk. Why this example? To lock in a key insight: bias is not always obvious discrimination. Often it's subtle, systemic skews in how and on whom a model makes mistakes. Our governance task is to surface those skews. Let's align on language first. Bias is not random error, it's systematic error that repeatedly harms the same group. Fairness may seem like the absence of bias, but it isn't that simple. There is no single, universal definition of fairness, and as we'll see, fairness depends on perspective. When we hear AI bias, we immediately think of legally protected attributes: race, gender, age, and we're right to do so. That's critical. But the problem is broader and deeper. Consider this example: someone risked their life to save a child from a burning house. Local news reported a heroic act. A year later, their life insurance premium doubled. Why? The insurer's algorithm didn't see heroism, it saw markers of risk-seeking behavior and disregard for danger. The model wasn't biased by race or gender, it was biased by data that, to humans, mean one thing, and to the machine, something else entirely. Our job in AI governance is to find not only obvious discrimination but these hidden conflicts of interpretation. So where does bias come from? It's a mistake to think bias is just bad data. Bias can creep in at any stage. Data, the most obvious source, brings three families of bias. Historical bias: data reflect real-world discrimination. For example, historical executive hiring data with very few women. Representation bias: some groups are underrepresented in the dataset, which degrades the model's accuracy for them. And measurement bias, also known as proxy bias: this happens when we substitute missing individual data with group proxies. For example, lacking income data, we might use a zip code, assuming that people in prestige neighborhoods have a higher income. The model learns that people from a poor area are a risky group, applying a stereotype to every resident, including a perfectly creditworthy person. But even with perfect data, problems can arise from the model and its training process. First, there's labeling bias. This occurs when human annotators, who create the correct answers for training, unconsciously project their own stereotypes. For instance, a content moderator may tag comments written in an unfamiliar dialect as aggressive more often, polluting the gold labels for the model. And even if the labeling was perfect, algorithmic bias comes into play. An optimizer trying to minimize overall error can amplify even small imbalances in the data, because that's often the easiest way to boost accuracy on the majority group. Finally, the deployment stage can create a vicious circle of interactive bias. Here, a model's predictions start to influence the real world, which in turn creates new, biased data. Imagine a patrol allocation system that sends more police to a neighborhood it labels as high risk. More patrols lead to more incidents being detected. This new data is then fed back to the model, which confirms its original belief, and the bias compounds. The bottom line: you need to verify everything, always, from the initial data collection to post-launch user behavior. So, how do we measure fairness? Mathematicians have proposed dozens of metrics. We'll look at 3 common ones, using a credit lending model as our example. First is statistical parity, also known as demographic parity. The idea is simple: the share of positive outcomes should be equal across all groups. If we approve loans for 15% of men, we must also approve them for 15% of women. This is simple, but dangerous. If true creditworthiness differs between groups, enforcing this parity means either denying qualified applicants in one group or approving risky ones in another. Second is equal opportunity. This is a more nuanced approach that focuses only on the truly qualified candidates. It requires that the rate of correct positive predictions, the true positive rate, be the same for all groups. The idea is that among all people who can actually repay the loan, the probability of being approved should be equal, regardless of their group. Instead of focusing on equal totals, we focus on ensuring that opportunity is equal for those who deserve it. Third is calibration. This metric focuses on the honesty of the score itself. If the model predicts an 80% probability of repayment, that number should mean the same thing for everyone. For example, that 8 out of 10 people with this score actually repay their loan, regardless of what group they belong to. Calibration makes the model's predictions equally trustworthy across all groups. So which metric is best? Here's the kicker: it has been mathematically proven that it's impossible to satisfy all these fairness criteria simultaneously if the base rates of outcomes differ between groups. You must choose. This mathematical fact is what makes fairness a governance problem. Since you can't have everything, your organization must knowingly pick a path, understanding the consequences and documenting the reasons for your choice. Now that we've covered the theory, how do we manage this complexity in practice? We use a 3-pillar framework: people, technology, and processes. Let's start with people. Let's be honest, bias doesn't come from silicon, it comes from us. Our history, our blind spots, and our unconscious stereotypes are what fuel the algorithms. If people are the source of the problem, they are also the main solution. It's impossible to build a fair system with a homogeneous team working in an ivory tower. The only working remedy is diversity and inclusion, applied in 3 directions. First, team diversity. People with different life experiences, from different cultures and backgrounds, will spot potential issues much earlier. Second, bringing in domain and ethics experts. Sociologists, lawyers, and human rights advocates can reveal non-obvious risks that engineers might miss. And third, and most importantly, engaging with affected groups. The voices of those who will be impacted by the system provide the most valuable signal about potential harm. Best practices also include inviting independent auditors or dedicated AI-red teams. Next, technology. We've gathered the right people, now let's give them the right tools. A full toolkit exists to mitigate bias, which can be grouped by the stage at which they are applied. First is pre-processing, which happens before training. The goal here is to fix skew directly in the data. Common techniques include resampling, where we add more examples from underrepresented groups, and reweighting, where we assign more importance to examples from certain groups. These methods are simple and effective, but they risk distorting reality or losing valuable information. Second is in-processing, which happens during training. This is a more powerful, though more complex, approach where we bake fairness requirements directly into the model's learning process. We add constraints or penalties to the model's objective function, forcing it to optimize for both accuracy and fairness at the same time. The price for this power is often a reduction in overall accuracy and a more complicated training process. Third is post-processing, which happens after training. This is like a cosmetic fix. We take an already trained, possibly biased model, and simply adjust its outcomes. For example, we could set different decision thresholds for different groups to equalize the outcomes. This is the fastest method, but it only treats the symptoms, not the root cause of the bias. There are production-ready libraries for all these methods, like Fair Learn from Microsoft and AI Fairness 360 from IBM, but remember, tools don't choose the trade-offs. People do. That brings us to our final pillar. Finally, processes. Now we have the right people and the right tools. But without clear processes, none of it works. There are three core processes that make fairness part of your system's DNA. First is the fairness decision process. As we've learned, you cannot be fair to everyone in every way. This process is about making a deliberate choice. You must select which fairness metric you will optimize for and what trade-off you are willing to accept. This decision must be recorded in the AI system passport and applied across the entire lifecycle. Second is the fairness audit loop. This is a regular, scheduled health check of your system for bias. This isn't just about measuring your target metric, it's about creating a full fairness dashboard with various risk indicators. This process ensures that fairness isn't a one-time pre-launch activity, but a recurring procedure. Third is the fairness incident response process. Even the best systems can fail, and development teams often miss problems that are obvious to users. This is a two-way process. First, you need an incident response plan with clear triggers and actions, up to and including an immediate shutdown of the system. Second, you need a real user feedback channel, a kind of fairness hotline for people affected by the system. How does this all work together? These processes don't exist in isolation, they plug into what you already have. The choices from the decision process go into the AI system passport. The risks identified during audits flow into your company's AI risk register. And the incident response plans align with your existing accountability matrix, like a RACI chart. Real governance isn't having a pretty document titled AI Fairness Policy. It's when an engineer knows, if this feature's correlation exceeds the approved threshold, I must obtain formal approval before using it. That's governance that works. Let's recap. Today, we moved from an abstract ideal to concrete, manageable tools. The key takeaway is this: fairness governance isn't about finding a perfect technical fix, because one doesn't exist. It's about building a managed process where your organization can make informed ethical and business trade-offs, document them, and own the outcome. Thank you for your attention, and see you in the next lesson.